Thanks. All right, so of course the first question is, can you hear me without the microphone? Yeah? Okay. If you can't at any point, just tell me to speak up. So I'm going to talk about machine learning and comparing and contrasting it to statistics. So I think you may have heard similar things earlier this week, but that's fine. Just a little bit about my background. My training was in biostatistics with an emphasis in fMRI data analysis. So where did I learn machine learning? I didn't learn it in graduate school, but during my postdoc, I started reading through Trevor Hasty's book, the statistical learning, and there are other authors, he's not the only one, but started working through that in a reading group, and so basically self-taught, but I've spent quite a bit of time with those methods and other methods over the years. So maybe you're wondering what machine learning is, and I wasn't aware of this big sort of debate, I guess, that there is of what machine learning is and what statistics is, and if they're the same or if they're different, and somebody was telling me about it this summer. I tend to just ignore things like that because I don't think they're useful, but it could be useful for you. So just generally speaking, machine learning is a combination of ideas from computer science and statistics. I realize there are more dimensions to it than that. I'm simplifying it a little bit. And so I'm going to focus on basically how it differs from statistics, machine learning, how they're the same. And the first specific thing I'm going to focus on is if machine learning is just fancy statistics. So for somebody working in the machine learning field, it's kind of an insult to be like, oh, you just do fancy statistics. At least I think that's what my takeaway has been from reading a bunch of blog posts and listening to people's arguments about it. So I'm going to address that first, and that's important if you're considering going into machine learning because you need to figure out where to go. Do you go to statistics department, computer science department, engineering department, data science program? Also, is machine learning better? You know, if you're just running a bunch of regressions and that's getting you through your graduate career, do you need machine learning? What is there to gain from using machine learning instead? And I have a couple of examples of applications with neuroscience data. I had a bunch. I had to trim them out because I had to leave time for the next speaker, obviously. And then what keeps me up at night when I know somebody's transitioning from only running regression and they're like, hey, I'm going to learn machine learning. I'm like, that's great. And then I'm like, oh. But that's a dramatization. I'm all for diving in and just trying to figure something out. Just be careful, I guess. So I'm going to point out a few things that I've noticed, little pitfalls. Okay, so is machine learning just fancy statistics? Obviously, no. So the top link there is a blog post written by someone who's in the machine learning field. And they're like, hey, if machine learning is glorified statistics, then architecture is glorified sandcastle construction. So when I first read that, I'm like, ouch. You know, I hope statistics is a little more sophisticated than a sandcastle. But that's not the tone of the whole blog post. It's a really good post comparing and contrasting the fields. So that's from somebody who does machine learning. And then a statistician, on the other hand, they're looking at the field and they're like, well, are support vector machine and boosting classified as machine learning, while logistic regression is statistics, even though they're solving essentially the same optimization problems up to slightly different shapes in a loss function. And you're probably like, it's 9 a.m. and you just had a bunch of words that I don't hear a lot, and that's confusing. So what the statistician, Wasserman, is saying is, hey, yeah, we're doing the things that are slightly different, but they have the same goals. And he's not saying we're doing the same thing. His attitude is more, we're doing very similar things, and maybe we should be working together. At least that's the flavor of the second link there, which is probably a better way to view it. So let's back up, and I'm going to give you a very black and white distinction between what machine learning aims to do and what statistics aims to do. Obviously, real life is more gray, so then I'll talk about what that gray area is. So if you're running statistics, you're going to have p-values or some type of inference. Even if you're Bayesian, you have some type of inference built in. And so when I use the word inference, all I'm talking about is you don't just take your parameters at face value. You step back and you say, well, wait a minute, how much variability was in my data? And how can, in light of that, how can I view these parameter estimates? And when you're running statistical models, you have a model. There's a mechanism that you're trying to understand. How is this part of the brain, not going to say predicts, but associated with something that the subject is doing? Whereas machine learning is interested in prediction. So the important distinction there is the model, the importance of the model or the story goes away. So I have an example. This is not a real study. But let's say we're trying to look at my happiness, how happy I am, and how close I am to each of 3 different cats in my house. So throughout the day, my cell phone pings me. It's like, how happy are you? And I hit a little thing on the happiness scale. And then my cats are wearing little collars. And then the collars get pinged, and they measure the distance between my cell phone and the cats. So then I have these distance measures for each of the cats. So for example, maybe I'm really unhappy because I'm trying to sleep and the orange cat's annoying. So I try to get away from the orange cat, and I'm like, all right, I'm feeling a little better. And the orange cat's like, hey, I'm hungry. And I'm like, stop it. I'm like, I'm going to go over here and hang out with the purple cat and the black cat, and now I'm really happy. So this is the idea. And so even as I was doing this, I bet you're doing a statistical model in your head. And you're like, oh, as you get closer to the orange cat, you're less happy. As you get further or closer to the other cats, you get more happy. That's telling a story, right? So that's the statistics approach. We want to know what the relationship between each of these cats and my happiness is. And also, of course, we want to know if these relationships are statistically significant. Maybe one of the cats isn't important. So we run our linear regression in R. So we have our happiness, and then we put the distance of each cat. And then we get the output. And then this is where you're like, oh, parameter estimates, I'm going to start telling my story. Yep, sure enough, that orange cat, there's a significant positive relationship, meaning the further the cat gets away from me, the happier I get, right? Because it's positive and it's statistically significant. The purple cat, not statistically significant, it's not having an impact on my happiness, and there's a negative relationship with the black cat, meaning the further the cat gets away from me, the sadder I get, because that cat makes me happy. So see how I just told a story about cats using statistics? Right. And this is misleading, right? Because, well, you'll see this is misleading because it looks like cats are really important in terms of my happiness. I'm being very careful not to use the word predicts. Nothing here was a prediction. It's one of my hugest pet peeves, and one person here has probably experienced me in my lab as someone's presenting and they're like, and age predicted brain activation. I'm like, nope, it didn't. Like, you didn't run a cross-validation. It's not prediction. I'm like, you found an association. So these are all just associations. And I will keep interrupting those people. It's really annoying, but eventually they stop saying predicts. Okay, so same data set, but now I'm going to use a machine learning approach. So I'm going to collect a second data set. So let's say this model I just ran was based on day 1 of data, so I got pinged a lot. Okay, maybe if I got pinged 300 times, that would be pretty annoying. But just pretend maybe this is 1 week's worth of data. So I have the parameter estimates from this data set. So the idea of machine learning is how important these parameter estimates are. Can I reuse these parameter estimates on a different data set and predict happiness? Okay, that's not the idea behind a standard linear regression. The regression is if the cats are important, not whether the parameter estimates are correct. So machine learning says, okay, these parameter estimates, can I use these to predict happiness in a second week's worth of data? So I'm going to use these estimates, but I'm going to use the distance measures from a different week. And I'm going to predict the happiness in the new data. So did you already learn about cross-validation? Great. So this is really just half of a twofold cross-validation. So what I have here are my predicted happiness values and the actual happiness values. And you can see that it's not a very good result. If it was a good result, these values would lie on a straight line that goes through 0, 0, and has a slope of 1. Often folks use correlation with continuous measures. It's a flawed measure to use if you're trying to assess your prediction. I'll talk a little bit more about that later. It depends on the type of cross-validation that you're using, that it can be problematic. Russ Poldrack had a post on it a long time ago on his blog, and then Trevor Hasty saw it and wrote a follow-up on it. So don't assess your continuous values if you're using some sort of regression for prediction with a correlation. Typically, you use what's called mean squared error. So you just take the square difference between the predicted and actual values, take the average. I took the square root of it just to bring the units back to the happiness scale. Mean absolute error is also frequently used. So anyway, you can see it's off by around 2 units of happiness, but the scale only goes from about 0 to 10. So that's not doing a very good job at predicting my happiness. And that's kind of relief, right? If my happiness was completely determined by cats, what does that say about my life, right? So we're much more complicated than that. But we get very different results, right? This is now telling me that, yeah, that statistics model I ran, I had p-values and I could tell stories about the individual cats, but overall, kind of who cares? It is helping, I am able to somewhat predict happiness, but they're not good predictors of happiness. Does that make sense? So that's why I hate when people say predicts when they didn't do a cross-validation. Okay, here's a more in-depth comparison. This is from these lists. There are all sorts of versions of these lists. This is still keeping things kind of black and white. Machine learning is in this bin. Statistical modeling is in this bin. But I'll go through these and I'll show you where the crossover is starting to happen. So machine learning methods, you've used some this week, right? In Python? Pretty easy? Yeah? Not a lot of vigorous nodding. It is. I don't care if you thought it was hard. It was easy. The machine learning methods tend to be really user-friendly. You can put your data in, you get your predictions out, and then with a few tweaks, you can run a totally different classifier and check that out. But the goal in machine learning, again, is the predictions. So a lot of times when I see folks transition, they're like, I'm going to use machine learning. I'm like, great. They're like, oh, all I got was this accuracy. My brain of data was just boiled down to one number. I'm like, yep, that's machine learning. They're like, how do I put something back on the brain? It's like, it's not really what it's designed to do. So I'll try to talk about that a little bit more later as well, but the goal is in that prediction. It's more automated, kind of treat it like a black box. It depends what you're doing. If you want to do more useful things, you have to learn what it's doing. Like support vector machines, sure, you have an algorithm where you can dump your data and it gives you a prediction, but to actually understand what it's doing, you have to learn how the model's working. Overfitting is a huge issue to worry about. That's why we have a lot of regularization methods for machine learning. And I'll have some examples to help illustrate that. And the idea of generalizability, it's important in both bins. For machine learning, you want your predictions to generalize to other populations. And with machine learning, this is sad news. I do a lot of work in power analysis, or I used to, and I'm constantly telling people, they're like, I have 30 subjects. I'm like, sorry, you probably should have 100 or 200 subjects for a linear regression, looking at the correlation between brain activation and some sort of behavioral measure. Well, you need even more data for machine learning, and part of the reason why is folks hear the word big data, and they're like, yes, because I'm going to put all my voxels into this model, so it's really wide. So they call them features in machine learning. We think of them as regressors. So hand wavy, you can just think of them as regressors, but they're called features. So you have a ton of features, but if you still have your sample size of 30, you're asking a lot of your machine learning model, or your prediction model. So you actually have to have even more observations, and that's to help with the overfitting problem, and also because you're going to run that cross-validation. So on the other half, statistical modeling, parsimony is typically of interest. When I was taught linear regression many years ago, Occam's razor, the simplest model is the best model. So if something's not helping, you take it out and you stick with what's left and you use that to try to understand what's happening. And of course, interpretability is really important. And the parallel for you is when you run a mass, if you do fMRI, for example, if you run your mass univariate analysis and you run a regression for each voxel, you get a nice brain of weights and t statistics, and you can threshold them, and you can interpret kind of what's happening. That's what statistical modeling is for. It helps with knowledge creation, trying to figure out how things work. Inference is very important. We always want to worry about the variability of our data. We don't just take our parameter estimates and say, wow, it's a pretty steep slope. You have to view that in the context of the variance of your data. The population you're working with is also important here. Your model only applies to the subjects from which the population from which your subjects were sampled. Generalizability is important, but here the generalizability is slightly different than in the machine learning side. In the machine learning side, it's the betas. The beta estimates we hope will work well on different data. In statistical modeling, the hope is that the model will work well on new data. And with statistical modeling, in comparison to machine learning, you need less data often. So where things are starting to change, or not recently necessarily, but there tends to be more overlap, is that machine learning methods, there are some that are trying to be more interpretable. And this idea of thinking about how the variability is impacting things is being built into machine learning methods as well. So I think going back to this argument of machine learning isn't statistics, it's its own thing. It's not just glorified statistics. That's fine, and it's important to know, machine learning is different from statistics. So if you wanted to study machine learning, you're probably going to want to work with someone who really does. I'll get to that in a second, the differences in the fields. But I think instead of trying to differentiate the things, it's important to see what you can gain from each other. So what's left in that statistics tube that isn't included in machine learning currently? And likewise, what can machine learning give back to statistics? Machine learning is a lot newer in the sense of, it's been around for years, but now it's being used more and more. And so it had the ability to do new things with conferences and sort of that type of thing. So here are a couple of the differences. As I said, machine learning, the papers are driven by conferences. So a graduate student coming out of a machine learning program is going to have a lot more papers than someone coming out of a statistics graduate program, because that's generally not how a statistics program, you have like 3 papers maybe. So it's much faster paced, and it creates a synergy in the field because you and all your peers are working to get your papers done at the same time. I haven't been involved in this, but it sounds really appealing to me. And another nice thing about machine learning is there are some statistics topics where statisticians are like, oh, we're done, we figured this out. And the machine learning community is like, no, we actually have to do this better. And so they've made a lot of improvements to these methods. Statistics, on the other hand, does still have some topics that could be useful to incorporate into machine learning. And the one is the idea of the worry about uncertainty in the data. So I have a couple of examples. These, I think, are both from this Wasserman paper, but one is this idea of semi-supervised inference. So, okay, let's think of a classification problem where I have labeled data, and I know these belong to the red group, and these belong to the blue group, and I want to run some type of a classifier on it. So an idea for machine learning is, well, why don't you collect a bunch of unlabeled data? So you could imagine, I have my students I teach a medical image analysis course, and they do a classification problem at the end of the semester. And they have retina images that have to be labeled as healthy or diseased. So you could imagine maybe that takes a long time. You have to have an expert view the retina images to classify what type of disease the diseased ones have and to label them. But maybe you could just toss in a bunch of unlabeled images and grab the features for them, and that could help inform the classifier. So here, you probably already did it with your eyes. You're like, I bet all these unlabeled ones, all the black circles are the unlabeled features. So we don't know if they're red or blue, but you might look at this and say, I bet these are all blue, and I bet these all are red. So that's the idea. You can get kind of the shape of the clusters or whatever you want to call it, and that can help inform the classifier, find the boundary between these two groups. So that's something that was developed, but then a statistician, Wasserman, realized, well, when we do this, we're making an assumption that we're actually getting information from the unlabeled data. So they built in an uncertainty measure to help determine if they should be using the unlabeled data or not. So it's kind of combining both fields. So he's a statistician who tends to work with the folks in computer science, I'm assuming that's where they are, at his institution to doing machine learning, so combining the two fields. And another one, a simple one's Gaussian mixture models. So you have some distribution shown in red, and you would like to express that as a combination of Gaussians. So this could be used in clustering. A lot of clustering algorithms are based on this idea. So in the statistics world, they're like, mission accomplished. We have tons of methods to do this. They're not guaranteed, but that's to find that absolute solution, but that's fine. That's just how life is. So they're done. They have methods for this. But in the machine learning community, they're like, no, actually, we need to do this, but we need it to be really fast for huge data sets. And that speed has to be guaranteed. So that's the improvement that's being done. And of course, that improvement could also benefit the statistics community. So I think we should focus on those fields working together. But again, it is always important to have labels for things to know how they differ. And that might, again, be important for you if you're choosing a graduate program or something like that. And this is from, there's a documentary called Animal Odd Couples, not to be confused with the TV show, because the documentary is way better. And this is a cheetah and a dog, and they were raised together when they were little babies, and they're buddies. But I think that's, instead of these arguments I see, one blog post I saw, it was just really harsh. It's like, you don't even need to know statistics to do machine learning. And then they kind of, later on, they're like, well, but if you really want to do stuff, you should learn some statistics. And then at the very end, after probably a lot of people were angry in the comments about that and other things, they had a big update. They're like, okay, I don't think this is, I think I was a little harsh. So I think that type of argument's not useful for either field. But in terms of figuring out where you want to go, it is useful to know how machine learning and statistics generally differ in terms of what you want to do. So questions so far? All right. All right, so is machine learning better? So what can we gain from using machine learning methods? So I tried to draw attention earlier to the fact that the betas and how well they generalize, that's the machine learning focus, whereas the regression focus is on the model, which is in red. So whether the x's and the y form a good model. But machine learning can help us understand the true usefulness of the theory. So with the cat example, running the extra step of the prediction with the cross-validation kind of highlighted how important the cats were in truly predicting my happiness, and they weren't that important. So here's another example. I feel like this is not to rain on your neuroimaging parade, but a lot of times I'll get pulled into projects. One was for football players who get hit. So they have a traumatic brain injury. So they have all these little tests that they do immediately after the injury to assess how bad the injury was. And they're very simple, cheap tests, and they actually work really well in predicting their recovery and how they're going to do. But they're like, we want to throw in an MRI and see if we can use the MRI to improve our prediction of how they're going to perform. And I was just like, okay, but your cheap little thing that you do immediately after, that seems, MRIs are expensive, right? So that's kind of this idea. So this isn't football players, but the idea here is you want to predict if adolescents are going to be binge drinkers at the age of 16. So what you do is at the age of 14, you collect some data, some behavioral, genetic, and neuroimaging data to see if that can be used to predict their drinking state at 16. And the accuracy that they got was 70%, which is pretty good. But one variable that they left out because they knew it was just going to definitely drive the prediction model, if they threw it in there, was simply asking if at the age of 14, do you smoke? And that by itself had a prediction accuracy of 75%. So this very cheap, almost free question was a better predictor than the really expensive genetic and neuroimaging data. So so if your goal is if you're honestly just trying to figure out if you need to do some type of intervention with this kid, just ask them if they smoke. You don't need to put them in the MRI. So see, the difference here though is the mechanism isn't really as important, right? You just want to help this kid. And I think for a lot of what we do, if you want to help someone with Alzheimer's or something like that, you need to figure out if they're actually going to get Alzheimer's. You want to predict that. So I realize it takes a step back from the mechanism driving it. Okay, did you guys learn about bias-variance trade-off already? Did Tal talk about it? Okay. I'll just skip this, just kidding. I'll go over it again. This may even be the same images he used because it's from his paper. But, what? Yeah. So I'll probably do it better anyway, but I'm just kidding. So, right, these are your estimates. The goal is to hit the target. Low bias, low variance means that your estimates are all very close to each other and you hit the target almost all the time. If you bias it, that means, but you still have low variance, the estimates are still very close to each other, but they're missing the target. And then we have this high variance, low bias situation. So the bias is low. Obviously the variance is high because the x's are very scattered, but the bias is low because on average I do hit the target. And last we have the high bias, high variance situation where it's kind of all bad. You're never going to hit the target and your variance is high. So do you remember when you took linear regression, the Gauss-Markov theorem? Oh, someone nodded their head. Just kidding. I'm not going to call you out. But does anyone remember what the Gauss-Markov theorem says? If a bunch of assumptions hold, you have your estimate is unbiased. It has the minimum variance, but it's like lawyer speak, right? Among all unbiased estimators. So it's not unbiased and minimum variance because that's impossible. It's just minimum variance among unbiased. So traditional statistics is always focused on the bias. Whenever I teach it, even if I weren't teaching machine learning, I always mention ridge regression because some people know what it is. And I say, well, sometimes you can actually introduce a little bias. You know, having bias isn't necessarily bad because you might have the payback of a reduction in variance. So so that's what I'm going to talk about. But again, the importance is traditional statistics is always focused on unbiased estimates. And that's not always good, especially if you're trying to do prediction. All right, so the sum of squared error, so your overall error, how far on average the squared distance between your estimates and the bullseye is, can be decomposed into the variance, how scattered those are around the mean of those data points, and the bias, how far that mean is from the target. So in a lot of machine learning textbooks, you'll always see, well, the plot I'm about to show you. But before I show you the plot of error and then the bias and variance decomposition, I'm going to show you how regularization can help. So on the left-hand side, the green line is the true function from which the data come, and the data are in blue. And then we have the model fit in red. So whatever this variable is, x on the x-axis, the model, it's a linear regression model, is a polynomial of degree 15. So x is in it, x squared, x cubed, all the way up to the x to the 15th power. Okay, so you can see what's happening is the line, since there are so many parameters, the fitted model almost goes through all of the data points. So that's what overfitting is. And you can see how overfitting is resulting in variance. We have a really highly, this thing's all over the place, right? So the variance is increased. Obviously, this red line is not going to do a good job of predicting in a different data set that's generated from the green line. Okay, so does that make sense? The idea of the overfitting? So if I instead use ridge regression, which is basically it's going to select some of the betas and it shrinks them towards 0. And you have to choose this lambda, which is a whole thing, but somebody who chose it for us, we'll assume they chose it in a good way that was not circular or problematic. But anyway, so lambda is found, so a certain degree of regularization. And you can see it smooths out this line. So it's basically starting with the same regression, but then there's this extra restriction put on the betas. And so now it's a lot smoother, and this is going to do a much better job predicting a new data set because it's smoother. So what's the bias? The bias is instead of letting each beta estimate be whatever it would be in a traditional regression, ridge regression says, no, I'm going to shrink you towards 0. So that's the bias. It's biasing the betas towards 0. Okay, so as I said back here, this can be decomposed into these 2 bits. So what that looks like is this plot. So we have error on the y-axis and model complexity on the x-axis. So there are different ways to think of this. You could think of the model complexity as changing the regularization on the ridge regression, or you could think of it as adding more and more regressors to your model. So if you sum these 2 lines here, this is the variance. So you can see as model complexity increases, you're going to get a much wigglier fit due to overfitting. So the variability is going to increase, and the bias is going to decrease, and you have the same overall error. Now, in the linear regression world, we're doing explanation, we're out here. So we're fitting all 15 parameters, say. So the model complexity is really high. So our prediction error is actually really high. So even though our bias is really low, who cares? Because the variance is so high, our overall error is quite high. This is, again, why it really bothers me when people run a linear regression and use the word predicts, because in fact, it's probably a horrible predictor. Because you're in this bin down here where you're unbiased, but the variance is likely high. And again, it depends on your sample size and things like that. If you have a ton of subjects, it's less likely to be the case. Whereas in machine learning, you're focused on prediction and you specifically try to minimize this error. So you might be introducing a little bit of bias, but look how much lower the variance is in return. And that is going to help make your predictor work better. That is the difference being here, relates to this graph, and then this graph on the left is when you're over here. Does that make sense? Okay, so that's the big difference. Questions about any of that? Okay. All right, so a couple of examples from neuroscience. Did Tal already talk about his own work? Okay, so this is something Tal did. And the idea is you measure somebody's agreeableness and try to predict their response to appeal a charitable donation. So they made up these little stories. So Daniel has lung cancer, only smokes cigarettes on weekends. When he went out in high school and college, he attends church every Sunday, and he has a reputation of somewhat of a gossip. So the subject is given this, and then presumably they have to rate whether or not they would donate to some need. So these hardships that were generated were unique for each trial and for each subject. And the way they're designed is you basically, or not hardships, but little scenarios. You randomly selected from a set of hardships, a set of photos, a set of names, and other things, and then you put them all together to make this little story. So the issue is, how do you norm the stimuli then? Because to norm something, you need to present it to a lot of people, and then you can use that information to norm it. But in this case, this is only seen by one trial for one subject. So what they did is they realized, well, the hardships are used over and over and over again. So the constituent components are used over and over again. So the goal was to establish that if the components could predict the the scenarios that were put together. And once they establish that using machine learning, they're able to norm using the components instead. Does that make sense? So that's pretty clever. So when, I should say, a lot of times when I'm working with, I work with a lot of graduate students and postdocs at my job, and someone will be applying for NRSA or NSF, I forget which one, but you have to have a training component to that grant. And they'll be like, I would like to learn machine learning. That's the thing I want to learn. And I always step back and say, why? What are the questions you're going to answer? They're like, I don't know, I already compared, the people I work with do a lot of meditation research. I want to compare meditators to people that don't meditate. I'm like, okay, but you already did that with the linear regression or linear models. Like, what do you expect to gain from machine learning? Like, I don't know if I can predict it. And that is useful. We saw how that is useful earlier. But I think if you're going to use machine learning, you kind of want to stretch your brain out a little bit and think about new and interesting hypotheses that you can look at, as well as diving a little more deeply into, all the times you've been saying predicts and you weren't really predicting. You can go check that, like, how was the prediction? But then you can think of other interesting ways to use these machine learning techniques. And this is an example of one of those. Another example, and there are a couple that are kind of this flavor, is this idea of brain age. So I want to warn you, there are a lot of algorithms out there for brain age. When I say a lot, I can think of 3, but there are a few. Just because a tool exists in software and you can download it and calculate brain age, be careful and always do some extra checks. This is the one I found that I thought worked pretty well. So I had asked Russ at one point, because somebody I worked with, she studies asthmatics, and she wanted to look at their brain age. So I'm like, oh, I'll ask around. So I asked Russ, you ever work with brain age? He's like, oh, I use this one algorithm on my brain. So you know how he scanned himself a ton of times? So he has a bunch of structurals. He was fine. He was healthy. It was all over a year. His brain age should not have fluctuated. So the one algorithm had him between like 30 and 80 years old over the year. So even though it's a published paper, there's a tool and you can apply it, it's not working well, right? So this one I applied to him at his data, and it actually was pretty close. So then I told my desk neighbor, I'm like, hey, use this one. But I had read this paper, and it's a great paper. They're very clear. I think they reported the results really well. So again, if you're using, this is another way to use machine learning. Somebody else did the work and you're just implementing it. Or you could do something similar to this on your own. Right, so the reporting was very useful. Oh, wait, I'm going to get to that later. But anyway, so here's the actual age. These are healthy subjects. So their brain age, which is on the y-axis, should be really close. And you can see that they plotted the important line, because correlation, even though they report a correlation, nothing makes me more upset than when I'm reading something and they only report correlations between the predicted and the actual values. I'll talk more about that. But here they have layers of information. They have this dotted line, which is the line with a slope of 1 that goes through the origin, and I can see all the points are very close to that line. And it actually pointed out something else that's important that I'll talk about later about the predictions. But then they also have mean absolute error, they have r squared, and then the root of the mean squared error, which is the other metric that's often used. So this is really cool, because then what my coworker did is she calculated brain age in her asthmatics and her healthy subjects, and then checked to see if there was a difference between the two groups, and there was. So did she run machine learning? No. This person did, using really complicated machine learning algorithms, and on 2,000 subjects, which is hopefully enough, and then she just implemented it. That's clever. And there are other methods that are similar to this. So TOR's neural pain signature is very similar. There's basically a map, and then you can combine that map of weights with your map of brain activation for somebody who's having a painful stimuli, and you can get a measure of their pain that'll be different than obviously asking them about their pain. So that's another interesting application. Okay. So what keeps me up at night? So just to be clear, it's not this bad. I'm not, if someone says they want to learn machine learning, I'm like, oh great, here we go. But I do keep an eye on them. I check in. Say, hey, how's it going? There was a graduate student when I was at UCLA, And she's like, I'm going to learn machine learning. I'm like, awesome, let's do it. And then she's like, my accuracy was 0.95. I was like, uh-oh. And like, oh, you had a peaking bias. So we found the peaking bias. And then like maybe a week later, she's like, my accuracy was 0.95. I'm like, really? So we found the peaking bias. And then after that, she's like, my accuracy is 0.8. She's like, something's wrong. So she eventually scaled back her enthusiasm. And that's how it's going to go. You're never going to learn something new and do it perfect the first time or the first 2 times or the first 3 times. Expect to make mistakes. You're human. Just have someone around to ask or find someone to ask to help go over what you've done. Okay, so the one worry is that I talked about this already, but you need even more data, which is discouraging for a lot of you, especially people doing clinical work. And again, as I said earlier, not just wide, but you also have to have more observations. And the reason is because it helps with overfitting. So here I'm not even using regularization, but you can see that here we have the overfit with a 10-degree model and only 20 subjects. If I have 200 subjects, the overfitting is less of an issue, right? So that makes it easier for your predictions to work well. This is, I hear, this has already come up this week, but this is probably the most frustrating thing, is we love running our models and putting something on the brain, right? We want to know what part of the brain was important. So this actually conveniently just happened, and this is not a dig against this person. They simply ran a support vector machine. It's probably the first time they've ever done it. Some numbers came out. They're like, I'm going to put those back on the brain. And they did, and they sent it to me, and they're like, hey, why are there are negative weights right next to positive weights? Like, that shouldn't be the case. And it's like, well, because this isn't a regression, you didn't run a mass univariate regression. This is a support vector machine. So how many of you have learned about support vector machines? Okay, how many of you understand what it's doing? How many of you know what a support vector is? Okay, it's interesting you're all over here. You guys go sit over there and you're going to learn about support vectors. So it's been a while since I've worked with it, but the only features, or in this case it would be voxels, that get betas are the support vectors. And they're not the ones that are like solidly in the middle of the cluster or whatever. They're the ones on the boundary, which makes sense. If you're trying to draw the boundary, you're going to use the ones near the boundary. So I don't even know what those parameters would mean. Right, so first of all, you're not going to have them for the whole brain. I don't know if that was the case here, or if they applied some sort of thresholding. And then the ones that you have, they're simply not interpreted the same as a linear regression beta would be. And again, the goal here, I realize they're trying to figure out what the brain is doing, but the goal of machine learning is to get that accuracy. So there are methods that have better interpretability. So maybe try to focus on those. There's a thing called a searchlight, but it's problematic. So I realize that's really unsatisfying, which is partially why I said earlier, try to think of new ways of looking at your data, because you've probably been doing GLMs, and I found out that that's a total neuroimaging. I said GLM in front of one of my old stats professors. He's like, why are you calling it a GLM? Regular regression, you've been doing forever, and you're used to that framework. This is a different framework, so you want to try to think about your questions differently. So kind of related to these weights is this idea of collinearity. So in the regression sense, do you know what you use to assess collinearity? Or do you worry about collinearity in your regression models? Why? What happens when you have collinearity? What? Yeah, the estimates get really unstable, right? One will be really big, and its collinear counterpart's going to be really small to balance things out. So we worry about that because our parameters might not even make sense in a standard linear regression. So yeah, they're definitely a problem in regression. They're still problematic in regularized regression, but only if it's designed to deal with that, and it almost uses it in a beneficial way. But it's only problematic if you're trying to interpret the parameters. So I'm to clarify that, I say that they're problematic, but only if you're then looking at the betas and trying to interpret them. Is that clear? Okay. But generally, these regularization strategies, what they do is they say, oh, these two variables are doing the same thing. I have an overfitting problem because the model is so complex. I'm going to throw out one of those variables and simplify the model. So that's kind of the idea of regularization. So let's go back to the cats. So let's say I just have two cats and they're siblings, little guy and a little girl, and they're like peas and carrots. They're always together. And so their distance measure are going to be highly correlated, about 0.95. So let's further say that the true regression parameter is negative 0.1. So for every 10 feet they get away from me, my happiness goes down by 1. Okay, so we're going to look at this not in terms of linear regression, but lasso regression. So lasso is a little bit different from ridge regression because it'll shrink the betas up to a certain point, and then it's like, nope, you're done, you're 0. So it will dramatically just shrink the beta all the way to 0, whereas ridge regression's more gradual. So what I did was I simulated data for 20 days, and I ran the lasso regression for each day to show you what the parameter estimates would be. Now, given this, is one cat more important than the other? No, they're the same. They're always together. So here are those estimates. These are the coefficients on the y-axis. These are the days, or the simulated days, on the x-axis. The brother cat's in pink, the sister cat's in blue. So the truth is where this is negative 0.1. And you can see the estimates more or less bounce around negative 0.1 on average, so great. And what else you'll see is look at where 0 is. So here, for a bunch of days in a row, the brother cat was chucked from the model by the lasso. And you might be thinking, oh, the brother was not making you as happy those days. No, that's not true. Both cats make me equally happy. All it is lasso decided the brother parameter wasn't necessary, so it set it to 0 because it's getting all the information it needs from the sister cat. Likewise, sometimes the sister gets chucked from the model and their beta gets shrunk to 0. And it doesn't mean the sister was less important that day. On average, it's going to be 50-50. Half the time sister goes, half the time brother goes. And sometimes neither cat is removed from the model. So you have to be very careful, especially when you're looking at the brain. You have high correlation between your features there because obviously voxels that are near each other are going to be highly correlated, and if you are on opposite sides of the brain, they're going to be highly correlated. So if things get removed, it's not because that part of the brain wasn't doing anything. Another part of the brain was probably doing the same thing, maybe, and so it gets thrown out. So you have to be really careful. And you'll see within the machine learning, some of the stuff I was reading, they're like, yeah, some machine learning models are highly interpretable, like the lasso, and some are really hard to interpret, like neural nets. It's like, oh, but be careful who you're telling that to, because if I say that to you, you're used to looking at those betas and interpreting, and that's not what they're saying when they say that. So, any questions about the cats? I don't really have sibling cats that do that. None of my cats like each other, so it's just mayhem. All right. So back to this example. Luckily, this paper was very clear in reporting because I noticed when I was looking at this graph, do you see anything weird about the predictions without reading the slides? It's on the slide, but the older people get predicted ages that are higher, and the younger people have predicted ages that are a little lower than their actual age. So overall, the mean absolute error looked great. The root mean squared error looked great. This correlation's great. Again, let's be careful about correlations. It looks like it's following the line really well, but you have to be careful about these things that are averaging. So when my friend was doing this, I was like, oh, can you check that your asthmatics are the same age as your controls? She's like, no, they're older. I was like, all right, let me know what your results are. So she ran it, and she's like, my asthmatic's brain age is higher. I'm like, all right, well, we can't run with that because it could be due to this bias that their predictions are going to be biased higher. Does that make sense? So it was an easy fix. We just put age in the model, and hopefully that resolved it. And they do mention it in the discussion section of the paper, but part of me was like, I wish I could have bold fonted that and like highlighted it, because if no one was helping her and she just ran it, I don't know that it would have dawned on her to look so closely at that plot and see that little uptick. She may miss that one sentence in the discussion section, and she could have ran with this like big story about this big difference in brain age. The effect still held, it was just a lot weaker after that. So if you're using these methods, just be careful, take a close look, and do, like in this case, like I said, I ran it on Russ's brains to see if it did seem like it was working well, to convince myself further before we actually chose this one to use. Okay, I don't like correlation. This is pretty obvious. These data, actual and predicted, are perfectly correlated, right? But if I look at the values, the predicted values are always 3 times higher than the actual values. So it's not actually a good predictor. So if you're reading a paper and they're evaluating their predicted values compared to the actual with a Pearson correlation, it's not enough. They need to put a lot more information, and they should be plotting things. Always plot so many plots. Just put it all in the appendix. I just love plots, and not bars with error bars. Like, don't do that. Use violin plots or data points. We want to see the data. So I can't recommend that enough. It's highly informative. Someone's going to look at it and learn something from your data. Okay. Oops, I think a little over, almost done. So cross-validation is not a cure-all. You can still suffer from overfitting. So in my class that I teach, the students have to, it's a medical image analysis course, they have these retina images, and they have to create features from the images. So they spend a lot of time just trying to extract how many flaws there are in the retina image and just get that number to use as a feature. And I was noticing as they were working on it, I'm like, oh, their cross-validations are gonna, like, they're definitely overfitting, because they would do it and look at how good the separation is. If they didn't have good separation, they'd do it again. So at first I was trying to prevent them from overfitting. I was like, be careful guys about overfitting. And I was like, you know what, I'm just gonna let them do it. And I'm not gonna penalize them for it, because at least they're utilizing the methods I'm teaching. But what I did do is, when I grade, I have a left out test set that they didn't have. But I always let them know how much their cross-validation accuracies, which were like 0.9 often, dropped when I applied it to the left out data set. And it often would just go down to like 0.6 or lower. For classifying healthy versus diseased retinas. So I let that be the lesson, the shock of how much lower their accuracies were on the left out data set. But obviously in real life, maybe you should have 3 data sets, one for feature development if you have to do that, one for the cross-validation, and one for the final test. But you just have to be very careful if you're developing the features, because you can start overfitting even a classifier with a cross-validation. Last, confounds are going to impact your data, your analyses differently. So in this work, there are 2 tasks, and it's a cartoon example. You obviously wouldn't run a study with 2 subjects, but there are 2 tasks, task A and task B, and this is the voxel activation. So they know that this task has a difficulty confound. Some people find task A to be more difficult, some people find task B to be more difficult. So the way we fix this is we just collect a lot of data, and the difficulty confound comes out in the wash, right? So it's going to average out. So this subject here, they find subject 1 finds task A to be more difficult, whereas subject 2 in green finds task B to be more difficult. Now, if I run a traditional regression, which is in the left-hand column, I would do the mean of A minus the mean of B for subject 1, which is about 5. And then the mean of A minus mean of B for subject 2, it's around negative 5.5. And then I combine those 2, I get something close to 0, and then it's not significant. So that difficulty confound averaged out, right? Well, if you're using machine learning within subject and you're classifying A versus B, you're going to get a pretty high accuracy. So it's 13 above chance for subject 1, and it's 13 above chance for subject 2. So that sign went away, right? That it was higher for one subject and lower for the other subject. And then when you combine those 2 accuracies, I'm just focusing on classification accuracy, you do get a significant result. But it's completely based off of the difficulty confound that we were hoping was going to average out. So the takeaway there is if you have a confound that's between subject, but you're doing your classification within subject, that confound's no longer going to wash out. But don't let that scare you. You should still dive in. This cat really does scuba dive. I don't know that it enjoys it, but be cautious and always ask for help. Always ask questions. You're all probably in a training part of your career. Don't be afraid to ask questions. Don't say you have a stupid question. Don't put yourself down, right? Just say, hey, I have a question. If I could get everyone in this room to stop referring to their questions as stupid, that would be great. And don't worry if you ask a stupid question. It's better than making a mistake or struggling with something for weeks because you're afraid you would look dumb if you asked about it. I worked with somebody and she would come ask me for help and I'd be explaining and I'm thinking, I don't think she gets this, but I can't help because she's not asking. It's my job to explain it well, right? But I can't if you don't tell me I don't understand what you're saying. You have to explain it to me in a different way. Instead she'd be like, I got it, and she'd leave. And then she'd come back a week later and ask the question again. And it drove me crazy. I'm like, it's fine, it's not your fault if you don't understand, just you have to tell me what you don't understand so I can try to explain it differently. So weeks went by to answer one question when she could have just kept insisting that I explained it a different way. So just ask for help, don't be shy about it. And in the end, so ignore the arguing between the fields, but you can focus on what we can gain by combining statistics and machine learning. Start thinking of different hypotheses and creative uses for machine learning on top of the simpler classifiers. And of course, be careful when using these methods. Use it with caution. So with that, I can take questions. My slides are there. If you want to look at them, I'm sure they'll post them here. If you don't have time to ask me questions, I'm leaving this afternoon, please email me. I don't care. You're not bothering me. If I'm busy, I'll just say, hey, I'm busy. I'll get back to you soon. Just use my Gmail, Jeanette.Mumford@gmail. That one's easier. I hate using Outlook, so that's where the whisk mail comes. So any questions about any of this? All right, well. You can ask me all your stupid questions later. Thanks.
JP 5 minutes. Let's do 5 minutes just to stretch your legs, go to the bathroom, and so on and so forth. JBS. No problem.
Well, I'm trying to be quick.
Yeah, no problem.
You think that
We have 50 minutes.
you think that we have to say you first said it.
No. How repetitive was it?
Oh, no, great.
No.
Oh, no, there's some things they're repeating also. No, I also.
No.
The first time it's not regularization.
Oh, I get it. Yeah. Yeah.
All right. Okay. No, that's.
Okay, totally.
Yeah. I had so only thing to do SPM. So as long as you don't input the direct, just the magnitude.
Do you have HDMI? How are you doing? I wish I had.
But it was also, there were other classes that didn't get it. That aren't supervisors that will and they could be in the middle of, if you think of like a cloud of data points, clustering, they could be in the middle, like safely in there, like there's so characteristic into that.
Yeah, but that's just like how I mean, once like when you want to predict, like if you now have a range image and you want to predict whether it's class A or class B, you have a dot product of space.
I agree, that's definitely what you do.
Yeah, so which means that if you have like a very high volume